First, change the speed of this video to 2x. I always give this advice before any one of my lectures because I think it would help you not losing your focus. So this is the LS166 shift register, different representations, and this is its internal architecture. If we draw a rectangle here, you see that we could see why we have these different representations. From A to H would be the inputs, and then other pins, and also the output QH. To understand the behavior of any chip, the best way is to look at the data sheet and its internal architecture. In here, I have drawn the truth table of the different gates used in the internal architecture so that you could follow along as we move on to understand the behavior of all the sections. So first, let's say that this clock inhibit is equal to 1. Based on the truth table of the OR, if one of the inputs is equal to 1, then the output is always equal to 1, doesn't matter what the other input is. So if we have the clock inhibit equal to 1, the output of this OR gate is always 1. We have a NOT gate here which would change the 1 to 0, so you would have a 0 here. This 0 is connected to the clock pin of all the 8 flip-flops in here. Therefore, the output would never change. You see, these are the flip-flops. The output would change on the low to high transitions based on the inputs. So in here, if that doesn't change, if the clock doesn't transition from low to high, then it means output doesn't change. It always remember its previous values. So let's put this clock inhibit equal to 0 so that the clock would transit, and therefore this output which is connected to the clock would also make the transition, and see how the behavior would change. The behavior of this architecture, this shift register, depends on the value of shift load. If the shift load value is equal to 0, let's see what would happen. So if we have a 0, this NOT gate would cause here to be 1. I put 1 on all the wires that this 1 is connected to. So we have a 1 here, and we have a 1 here, and so on. So let me also wipe these things out. I was testing it before. So also this 1 would go through another NOT gate, so we have a 0 here. Based on the truth table of the AND gate, if one of the inputs is equal to 0, output is always equal to 0. Therefore, we would have a 0 here. One of the inputs is 0. Doesn't matter what the other input is. You see, it doesn't matter. Serial input is the other input. Right now, if the shift load is equal to 0, it doesn't matter what the serial input is. Now, in here, as you see, A would go to the other input of this AND gate, sorry. Again, based on the truth table of the AND gate, if one of the inputs is equal to 1, then output always follows the other input. If the other input is 0, output is 0. If the other input is 1, output is 1. So if we have one of the inputs as 1, output is always the other input, which is A. So right now I have 0 OR with A. Based on the truth table of the OR, if one of the inputs is equal to 0, then the output always follows the other input. You see, 0 would give a 0, 1 would give a 1, based on the condition that one of the inputs is always 0. So if we have A0, A or 0, it means the output of the OR gate is always the other input, which is A, and goes through a NOT gate. We would have an A here. This A would go through another NOT gate. So, sorry, it would be the NOT gate of A. As I said, it went through one NOT gate. So I have A here, and therefore I have A here, and also it is connected to the R, so I have A here. Now, the same thing applies to all of the others. You see, this 0 would go through this wire to one of the AND gates. So we have 0 here, B comes here, and we have B here. 0 or B, we would have B on the output of the OR gate. We have a NOT gate. We would have the NOT of B, and therefore we have the B itself. And this happens for all of them. We have C, we have D, and up to the all values. Now, when the clock makes the low to high transitions, the QA would be equal to A, QB would be equal to B, QC would be equal to C, QD would be equal to D, and so on up to the value of QH, which would be equal to H. And let's say that we actually did that we actually made the clock inhibit equal to 0. The other clock would make the transitions. We also made the shift load equal to 0 first, then the transition happened, and then therefore the QA to QH has been equal to A through H. And this is actually what is being done. I later give you the example of where this shift register is used. Now let's say that we put the shift load equal to 1 and see what would happen. So if we have shift load equal to 1, the NOT gate would cause that we have a 0 here. So we have a 0 here, we would have a 0 in here. It doesn't matter what the other input of this AND gate is. As you see, A right now doesn't matter. The output of this AND gate is always 0 based on the value of shift load. So we have this 0 would also cause us to have a 1 here, and the serial input, which I call it S, we have S and 1. And based on the truth table of the AND, again, the output follows the other input. So we would have S here, which therefore causes us, let me just wipe these things out. Therefore, we would have S naught in here. You see, on the output of the OR gate, we would have S, and the NOT gate would cause it that we have the complement of S, and therefore we would have the S itself in here. What about others? Well, the 0 is connected here, we have 0 here, we have 0 here, we have 1 here, but in here, the other input of this AND gate, as you see, is QA, and previously we put A value on the QA. So we have A here, A, and with 1, we would have A here. And A or with 0 would be obviously A, but goes through another NOT gate, which we would have the complement of A, and therefore we would have the A itself here. And the same thing would be applied to the all others. You see, B in here has come through this AND gate, so we would have B here, we would have a 0 here, therefore we would have the B naught, and therefore we would have B here. The same thing applies to all the others, but now the low to high transition of the clock happens. Now what happens? Now the QA would get any value which is here on the low to high transition, which is S. So here we would have S. QB would have any value which is here, which therefore would be equal to A. QC would be equal to B, QD would be equal to C, QE would be equal to D, and so on. QH would obviously be equal to G. Again, you could just understand it by saying, well, we made the load equal to 0 previously, the shift load causing the G to have the value of G. This value is the input of one of the AND gates. We have G here, the other is 0, the other, sorry, is 1, so we would have a G here, we would have a 0 here, and so we would have the complement of G here and the G itself as the one of the inputs. On the low to high transition, this G would travel to the output, so QH would be equal to G. This was on the first low to high transition. On the second low to high transition, as you see, they would travel further, meaning now QB would be equal to S, QC would be equal to A, QD would be equal to B, and so on. Obviously, this time QH would be equal to previous value, which was F prior. So it's shifting the different values up or down depending how you look at things. Right now, I want to show you two things. One of them is obviously what I have summarized here, that if clear pin is equal to 0, all of them is 0, is just overwrite everything. Clock inhibit is equal to 1. QA to QH would all remember the previous values. If you are working with the chip, obviously you have access to the last output, which would be the previous value of the H. If SL equal to 0, whatever is on the input would go on all the outputs. These outputs doesn't come out of the chip. One of the outputs come out of the chip. But when you make the SL is equal to 1, then all the values would be shifted down by one value on every low to high clock transitions. The other thing which is so important that I wanted to show you is where this shift register is used. This shift register is in fact used in both the motherboard and the graphic card of the IBM PC 5150, which arguably is the first PC ever made. And this is actually the graphic card that I have drawn all of it on the tablet in here. I also have a course about the motherboard at the wire level, the motherboard of the IBM PC with the link in the description that you could understand everything on the wire level. You see, it just talks about the beginning. This is the graphic card to when the monitor would scan pixel by pixel. And if we look, this is the LS166 shift register. And as I said, the way it works is that 1 clock out of 9 clocks, SL would go low, the shift load. Therefore, whatever is on the input would go on the outputs, all the QA to QH, which obviously you don't have access to. But then for 8 clocks, the S would be equal to 1, and on the low to high transitions, the value that we put on the Q to H would travel, and therefore QH would at 1 clock would have the value of H, on another clock would have the value of G, on another clock would have the F, up to the value of A. And all the others here would have some meanings. This is really complicated. Let me know if you want to understand the graphic card at the bit level. I don't think there is any lecture or course or even book explaining about these things. I had to almost reverse everything from the manual and the datasheet.